You may be wondering why I jumped from maximum likelihood estimation right into exponential families, and the reason is that it turns out that the MLE, the maximum likelihood estimate for an exponential family, I'll just write expfam, satisfies a very elegant property, and this is one of the marvelous, beautiful properties of exponential families. So in order to prove this, I wanted to introduce exponential families, and I don't remember exactly how this calculation goes. So let's see what happens. All right, let's assume that our exponential family is in natural form. So remember that means that the probability. So here, it's going to be a distribution on RD. So our x is going to be in RD, and let's say theta is in RK. So this thing is e to the theta, since for in natural form, this function, this vector valued function eta of theta, is just theta. So this is e to the theta times s of x. S is a vector valued function, times h of x for some non-negative function h, divided by z of theta. So that's what we're working with here. This parameterizes our exponential family, and we want to compute the MLE. So how are we going to do that? So let's set things up for an MLE. We've got some data, x1, x2, up to xn, and each of these is some xi in RD. And we want to compute theta MLE. What is that? Well, that's just by definition the argmax over thetas, and this is over thetas in that set. We have some set capital theta, subset of RK, that these thetas live in. Argmax of the probability of the data given, not x, given that theta. So first thing we need to do is come up with an expression for this. So I'm assuming, as usual when we're computing an MLE, that we've got some sequence of random variables x1 through xn that are distributed according to this distribution, p sub theta. And so by this I just mean the probability that x1 equals little x1, x2 equals little x2, and so on. And so this thing, let's see if we can figure out an expression for this. Let's first look at a single x. So this is just some generic x in RD, given theta. Oh, well, of course, oh, right, well, that's just this. Okay, so that's just, by definition, that's this thing. P of x given theta is this. So we don't need to do that. Let's go ahead and compute the probability of our data given under some theta. And as usual, in the and I should have mentioned, these are IID, these x's. So this factors as the product, as usual, in this type of MLE calculation. The product of these, and what's that? Well, let's multiply a bunch together and see what happens. So we've got, let's write it out. Let's just plug that in first and then see what we get. E to the theta transpose. So this is the inner product, right? Theta transpose s of x. So this is the inner product, or the dot product, if you will. Theta x s of xi times h of xi divided by z of theta. And this becomes e to the sum. Well, let's put the x's out front first. Let's see, this is, what am I going to do here? Let's say it's z to the, put it this way, minus n, right? Z to the minus 1, n times the product of the h's. Actually, let me put that at the end. E to the sum, right now it's e to this, so product of exponentials becomes the exponential of the sum, and we can pull out this theta transpose times the sum as I goes from 1 to n, not si, sxi, times this product over h's, h of xi's. Okay. So now what are we going to do? Alright, we have our expression here. And now we want to maximize this with respect to theta. Let me give this sum a name. Maybe that'll make life a little easier. Let's call that well, let me just rewrite the whole thing here. Z of theta to the minus n, e to the theta transpose. I don't know, what should we call it? Let's call it S of d. That's pretty good. H of xi, product over i's. Okay, so now we want to maximize this with respect to theta. Now theta, remember, is a vector. Theta is a vector in Rk, so we need to maximize with respect to this vector. So let's do the standard calculus thing. We'll set the gradient equal to 0 and solve. So let's take the derivative with respect to one of these thetas. Let's say theta j of this expression. Oh, actually, let's take the log first. That'll make life easier. So, well, let's write what the log is. The log, especially for exponential families, I think, yeah, I mean, log makes your life much easier. So this is minus n log z of theta plus theta transpose s of d plus the sum over I from 1 to n of log h of xi. And now we want to maximize this with respect to theta. So the first thing to notice is that when we differentiate this, which is what we were about to do, we'll differentiate this with respect to theta j log. This is the log likelihood, because this is the likelihood, the probability of the data given theta is the likelihood function, so the log of that is the log likelihood. And when we differentiate with respect to theta j, first, this doesn't depend on theta j, so that just drops out. And what do we get here? We get minus n. I'll just put it, let's save this calculation, and we'll come back to that in a sec. Z of theta. And then here, this is this inner product, right, is just the sum over I from, let's say, j, from 1 to k, theta j times sj of d. Let's see, what's sj of d? Oh, sj of d then is just the sum. What do I mean by that? I just mean the sum as I goes from 1 to n of the jth component of s. Remember that s is some vector valued function, so we can always decompose it into its components, s1 through sk, each of which is a real valued function on Rd. So we can define this thing, and this inner product Sd is well, yes, yeah, it's that, equals that. So if we differentiate this with respect to theta j, we get just all of them except theta j drop out, and we get sj of d. Okay, so that's looking pretty good. And we just need to figure out what the heck this thing is here. So what is that? What is the derivative of log of z of theta. And remember, I called z of theta the partition function. So let's see if we can compute this thing. So this is an aside. This derivative, log z of theta. But what is z of theta? Z of theta is it's the normalizing constant for this distribution, right? We have this distribution, e to the theta transpose s of x times h of x, and z is just the normalizing constant. We could have written this p sub theta of x is proportional to this part and left off z of theta. And you can always recover z of theta by integrating. It's a probability distribution, so it has to integrate to 1. So you can always solve for z of theta by integrating this part and setting z of theta equal to that. So I'll write that down here. So z of theta equals the integral over RD of what do I want to say? E to the theta transpose S of x, h of x. Because if we divide by z of theta, then this becomes the p sub theta of x, and it has to equal 1. And this is integrating with respect to x with respect to Lebesgue measure. And this now, okay, so we have the log of this. So the derivative of a log equals 1 over z of theta times the derivative of z of theta with respect to theta j. And if we differentiate this, let's assume that things are nice enough. Let's assume that like h is nice enough here and s is nice enough that we can differentiate under the integral sign. That sort of standard sort of trick. So if we assume that things are nice, let's say, assuming everything is nice and smooth, that's what we need. We need some smoothness to do this. Then we can differentiate under the integral sign, and we get the derivative of this. We move the derivative inside, and it's the integral. So the e to the theta. So this part stays. This isn't affected, but we get an we get sj of x, right? We get sj of x because the derivative of this we recall we computed that already, and that's just sj. Well, the derivative of theta transpose s of x is, by the same logic, is sj of x, the jth component of this vector valued function, times e to the theta transpose, so it's just everything else, h of x dx. And now, right, okay, so now we move the z of theta inside here, and that, this divided by z of theta is just our original distribution. So this equals sj of x times p sub theta of x dx. And that equals the expected value of s sub j of x, of the random variable x that distributed according to this probability distribution. So it's the expected value of the jth coordinate. And maybe I should put theta here to emphasize that this is, when x is distributed according to theta. All right, so I'm running out of time. Let me stop here, and we'll be back and finish computing the MLE for a exponential family.